Alright, so today we will continue to our second tutorial. Okay, our previous tutorial is on introduction to number system and logic gates. Okay, previously we have studied on the binary number system and the association system. Okay, we have several number system like binary, octal, hexadecimal. Okay, we have learned in previous class for unit 1. Okay. Okay, for today we will continue to our syllabus for unit 2. Okay, I want to show my screen. Okay, I hope that you guys can see my screen. Okay. Okay, we have Boolean algebra and logic gates. Okay, for this topic, this chapter, we will be introduced to Boolean algebra, which is a branch of mathematics which will allows us to manipulate the logic between 1 and 0. Remember, we have logic 1 and 0 only of the binary system, and also on the minimization of the Boolean function. Okay, however, for the minimization of Boolean function, okay, we will discuss this on and the MSI combinational logic circuit. This will be on unit 3. Okay, as for today, we have 4 subtopics to be covered. For today only 3 subtopics. The first one is Boolean algebraic theorem, and second is built-in arithmetic circuit. Okay, and finally on the canonical form of the Boolean function. Okay, for this unit, we will introduce to Boolean algebra. What is it? What is the Boolean algebra? Okay, it is a branch of mathematics that allows us to do manipulation of logic between 0 and 1. Okay, in the binary system. Okay, and also to learn how to minimize the complex Boolean function. Alright. First is on the Boolean algebraic theorem. We have few laws for the Boolean algebra, and to apply the law, okay, the branch of mathematics called Boolean algebra was developed by an English mathematician. Okay, he is George Boole. Okay, in 19th century. Okay, based on the concept that assumption any proposition can have two possible conditions, either true or false. Okay, a preposition is just a statement which is either true or false. Okay, for example, we have true or false in only two conditions, which is true or false, or high or low, or 0 or 1. Okay, for example, a preposition is we say the cat in a box is that. Okay, we have a cat in a box and we say that the cat is that. Okay, it can be either true or false. Okay, if it is true, then the cat is indeed that. Okay, if the preposition is false, then the cat is still alive. Okay. Okay, between two conditions only. Boolean algebra is now widely used in the design of digital circuit. Okay, in logic gate, we use high and low states, 0 and 1. For example, we have A. Okay, input is high. Okay, let's say we have A equals to the input is high, which is true. Okay, if the input A is low, then we write as A bar. Okay, the opposite from the initial condition. If A is high or A equals to 1, then A bar is equals to 0. Okay, for law of Boolean algebra, okay, well developed and must be straightforward for in order we can use that. Okay, okay, we have used the Boolean expression like we have A dot B, A plus B, or we have in the exclusive, okay, exclusive OR. Okay, These are the commutative law for addition, multiplication. We have association. Okay, and this is the rest. Okay, this is being asked in the cost assessment 1, right? Okay. A Boolean expression is nothing more than a description of the input conditions necessary to get the desired output. Okay, these expressions are based on the Book's law and the theorem. The mathematical fundamental of all logic circuit and digital electronics is in fact that based on these laws and theorem. Okay, this commutative law. And we have commutative for addition, associative for addition and multiplication, and distributive and intersection. Okay, Boolean algebra allows the systematic arrangement of logic gates to produce the desired outcomes. We use the Boolean algebra to get the most simplest circuit. Okay, we do simplification. We want to construct a circuit to perform a task with minimum logic gates in order to minimize the circuit. Okay, we don't want to make the circuit become complex. Okay, the number of gate used will ultimately translate to cost. More logic, more components, meaning that okay, we will increase in the cost. Okay, lesser the gates being used or lesser the components, okay, the smaller the cost. Okay, and our system will be less complex. Okay, the first one is we have commutative law. Okay, we have the operator plus in Boolean term is the symbol of or this one here. Okay, dot is for and function. This is OR gate. Okay, we have either two input A and B. We also can write in B and A. Okay, and next is we have AND gate here. Okay, AB. Okay, same goes with BA. Okay, the commutative law of additions as implemented in OR gate, and this one is commutative law of multiplications as implemented with AND gate using two input and we have one output. Okay, so this is the symbol of circuit representation. Okay, next one we have the associative law. Actually, this one should be discussed before you submit for cost assessment 1, okay? Because it is in cost assessment 1 question. Okay, never mind. Okay, we just continue. Okay, now we have the associative law of addition. We have if we have three inputs, okay, we can write by this expression of circuit here of 2 OR gate. Okay, and also we can have in this term. Okay, this is the manipulation here. Okay, we can simplify by this and also by this. This one is multiplications for AND gate. We use 2 AND gate, okay, for 3 inputs and 1 output. Okay, this is for associative law of addition as implemented with OR gate, and this one as implemented with AND gate for multiplication for this one. Okay, next we have distributive law. Okay. Okay, in normal algebra, the distributive law we can write as this one here, A dot B plus C, and we also can write in terms of this. Okay, this one. This is when we factorize, we can get this, and this is when we multiply A to B and to C. Okay, this is how we can draw. Okay, can also be equally true for Boolean algebra as shown using the logic gates here. This is when we use one OR and one AND gate. Okay, this is also similar when we use two AND gate with one OR gate. Okay, this is this is the distribution law as implemented with logic gates and OR. Next one we have intersection law. Okay, the law states that the A term and with one equal that term and with and equals to 0, meaning that if we have 0, 0 and it is equals to 0. Okay, if it is multiplied with any one okay, this unity, then it will get this original condition back. Alright, so this is the law of intersection as implemented with AND logic gates. Okay, anything multiplied with 1 will get the gates, will get the original condition, like here this one. Okay, and anything multiplied with 0 will get 0. Next we have law of union. Okay, the law states a term when we OR with 1 equal and a term when we OR with 0, we can get the equal. Okay, if A, we have A and 0, then we can get A. This is, remember, this is when we use OR gates, and this is when we use the other input is 1, so we get 1. Okay, let's say if A is 0, 0, add with 1, we can get 1. If 1 add with 1 also, we have 1. Okay, please remember that in Boolean, the variables can only have two values, okay, either 0 and 1. Since A can only be 1 or 0, then we substitute for A. Okay, if A plus 1 can either be 1 plus 0 or 1 plus 1. Okay, in either case, if we have A plus 1 equals to 1 or A plus A, if A is equals to 0, then also can get 1, right? Okay, so this is a law of union when we implemented with logic gates union of OR. Okay, next we have is idempotent law. Okay, the law states that the A term when we end with itself or with itself is equals to that term. Okay, meaning A multiplied with A, we get A. Like here, this one, we have two in A and we create two inputs, A and A is equals to 1. Let's say is equals to A. Let's say A is 0. So we have 0 and 0 equals to 0. If A is equal to 1, 1 and 1 also here is equals to 1. Alright, so this is for and this is for OR. Okay, same goes if it is 0, 0, 0 multiply is 0, we add with 0, we can get 0. Okay, if 1 add with 1, then we get 1. Okay, are you guys notice that both input here are same? Okay, because we use the same node. Okay, we use same node from this original input. Okay, and for idempotent law union, this is when we implement with and OR gates. Okay, next one is we have complementary law. Okay, for complementary law states that A term when we end with the component equals to 0 and when we OR with component equals to 1. Okay, let's say here we have for example, we have A bar equals to 0 and A plus A bar equals to 1. Okay, if here is A equals to 1 and this one here is 0 because it is, we have inverter. So 1 and 0 equals to 0. If it is 0, the converter is 1 here. So the answer is also 0. Okay, and when we use OR gates here, if it is 1 and here is inverter 0, 1 plus 0 equals to 1. If here is 0, here is 1. 0 plus 1 also equals to 1. So this is the complementary law implemented with logic gates and OR. Okay, you can see that it is quite easy to implement the expression into a circuit, but we need a NOT gate here. Alright, this is for complementary law. Next one, we have double negative law. Okay, for double negative law, we can use 2 times 4 inverter. Okay, here is we have double negative law, so meaning that we can get the original condition back. Okay. Okay, we do double negative law using 2 NOT gates. Okay, the double negative law implemented with 2 gates here. If it is here is 1, after we inverter, okay, here is 0. So another one, after another one inverter, it will become 1. Okay. For another condition, if it is 0, 1 and 0. Okay, that is how you can get the original condition back. Right, so that's for double negative law. And next one, we have law of absorption. Okay, A dot A plus B equals to A, or A plus AB equals to A. Okay, remember that A and B can only be 0. So we can write the law of absorption as this one here. Okay, let's say A equals to 1, 1 dot, and B equals to 0. Okay, 1 dot 1 plus 0. Okay, we get 1. Okay, let's say B is equals to 1. Okay, 1 dot 1 plus 1, also 1. So we can get 1. That is how we can get equals to the original condition back. Okay, same goes here. If 1 plus 1 dot 0, okay, meaning that here is 0, then we can get 1. If B is 1, 1 plus 1 dot 1. 1 plus 1, get 1. Okay, so that's for law of absorption. Next is, so we can write the law of absorption as A plus AB. Okay, next is law of common identities. Okay, we have A plus AB bar equals to A plus B, or A bar plus AB equals to A bar plus B. Okay, this is the two statements are based on the complementary law. Okay, so we have law of absorption like previous. A equals to A plus AB. Okay, for idempotent law, A equals to double A, AA. Okay, and for complementary law, we have AA bar. Okay, AA bar equals to 0. And for factoring, okay, we have this one. Okay, for factoring law and complementary law, and also we have the intersection law. A dot 1 equals to A. Alright. So we have the De Morgan's theorem. Okay, states these conditions for De Morgan's theorem. Okay, if we have this bar here, long bar, so we can divide into A plus B bar. Okay, if this one here, we can have this condition. Okay. Okay, we can write in two parts. This is the first part and this is the second part. Okay, so this is the examples of De Morgan's theorems. Okay, illustrate by logic gates. Okay, shows for the gates equivalent. Okay, let's say if we have A and B as the input and we use the NAND gate. This is NAND gate because we have this not inverter here. So we can have AB bar. We also can say that it is equals to this one if we have A and B after the inverter and we have OR gate. Okay, so this is the first conditions and this is the second one. We have AB. This is NOR gate. Okay, we have A plus B bar, and this is after we use AND gate, we get AB bar, right? So this is for De Morgan's theorem. Okay, in this section, the first subtopic, okay, we have looked at Boolean algebra in detail for each of the gates. Okay, in particular, we have discussed on commutative and associative. Okay, what else law? Distributive, the intersection, union law, idempotent, and complementary. Also, we have discussed on the absorption and common identity law of Boolean algebra. Okay, in addition, okay, now we should understand on how De Morgan's theorem and the gates associated with these theorems. Alright. So next, we go for the building arithmetic circuit. here we have the adders, okay, how we can use in block logic diagrams. Okay, in electronic computers, do mainly binary calculations in the operations. Now we will look at how arithmetic operations are performed by using the logic gates. Okay, the most basic of arithmetic operations involved is addition and subtraction. Okay, remember, the most basic is addition and subtraction. Okay, but how about multiplication and division? Okay, do you guys know that actually multiplication and division can be implemented by using addition and subtraction respectively? Okay, for example, okay, when we multiply 3 by 2, okay, let's say we multiply 3 by 2, okay, we are adding 3 to itself 2 times, meaning that 3 plus 3. Okay, that is multiplication 3 by 2. Okay, and when we divide 6 by 2, meaning that we subtract 2 from 6 for several times, meaning that 6 minus 2 minus 2 minus 2. Okay, until we get the remainder, until we want the desired remainder that we want, or until there is no remainder at all. Okay, so this is the basic element in computer arithmetic, and that we use adder and subtractor. Okay, then we will focus on these two, adder and subtractors. Okay, in next section. Okay, now what is the adders? Okay, this is name suggests to do the additions. We have quarter adders, half adders, and also full adders. Okay, all the adders are logic gates that take binary inputs which represents some numbers value, and then we put it together to obtain a summation. Okay, they are classified according to the ability to accept and combine all the digits. Okay, this is quarter adder. Okay, add 2 binary digits but will not produce a carry. Okay, let's say, okay, 0 plus 0 is equals to 0. This is basic 1, 2, 3, and the fourth one, 1 plus 1 is equals to 0, because there is no carry here. Okay, if we compare this with truth table from an OR exclusive OR gate, then we will notice the similarities, okay, from exclusive OR. Okay, so an exclusive OR gate is already a quarter adder. Okay, this one here. Okay, this shows that on how we can use AND to AND gates and OR gates to produce the desired results for quarter adders operations as we described here. Okay, let's put A is equals to 0 or B equals to 1, then we can have these conditions for quarter adders, which is approximate or equals to exclusive OR gates. Okay, next one is we have half adders. Okay, half adders circuit takes 2 binary digits on its input and produce 2 binary digits on the output, a summation B, and also we have a carry B. Okay, like here we have summation and carry at the output. Okay, so this is the truth table. Okay, from the truth table, we can see that the carry output C is 1 only when both A and B are 1. Okay, is it correct here? Okay, C is 1 only when A and B is equals to 1. Okay, the C output is clearly and the N function of the input. Okay, meaning that we use C as N function here. Okay, or C equals to A dot B. Is it A dot B? Then we get this condition. Okay, we can observe that for the summation output here is clearly an exclusive OR function of the input A and B. Okay, when it is the same input, A and B is 0. When the different input here, it is equals to 1. So this is an exclusive OR function. Okay. There are various ways to constructing half adders, as we can see. Next is this is how we can construct the half adders. Okay, we have exclusive OR and AND gate. We because this one is AND gate, C for input, and the summation is exclusive OR. Okay, that is how we can get this half adder logic gate. Also, we can have this is the same as equivalent as here. Okay, for half adders. Okay, it's either we use exclusive OR and AND gates, or 3 AND gates with OR gates. Okay, so this is the half adder logic diagram. Okay, since the carry out bit is a result of AND operations, we merely put an AND gate in parallel to a quarter adder to obtain a half adder. Okay, remember this one is quarter adder, meaning that this is quarter adder and we put a AND gate to get half adder. Okay, half adder logic diagram. Okay, next one is we have full adders. Okay, let's see for full adders. What is the operation? Okay. What do we do with the carry bit that generate in the half adder? Remember, for half adder, we have carry bit. Okay, carry bit. The carry bit generate from the half adder. Okay, obviously, okay, with a half adder, there is nothing much that we can do since it does not accept a carry input. Okay, but full adder does accept a carry input here. Okay, and uses that is its computation together with the two input bits as the truth table. Okay, we have two input A and B, and another one is C input B. Okay. So here we have A, B as input, C in as carry input bit, okay, and C is carry output bit and the summation bit, okay. So from this one, we can have the logic truth table. Okay, we can have truth table, okay, for this condition. And let's see the logic diagram. Okay, for here. Okay, we have the logic diagrams, the logic gates combination to make up a full adder, and the block schematic to show the relative positions of the circuit components. Okay, so here we have half adder, then this is another half adder. Okay, to get it as the output. Okay, the full adder is constructed with two half adders and an OR gate. This one. Okay, as shown, input A and B are applied to logic gate 1 and 2. Okay, this make one half adder. This one is one half adder. Okay, exclusive OR 1 and AND gate. This is one half adder. Okay, and the summation output of this half adder and the carry output from a previous circuit become the input to the next half adder. Okay, the carry from each half adder is applied to gate 5. This is another half adder 3 and 4, and both carry to gate 5 here to produce the carry out for the circuit. And we have the carry bit C has a state 1 as long as any two of A, B, and C in input has a state of 1. Okay, that is how we can get the carry bit C. Next one is we have the subtractor. Okay, subtractor circuit take only two binary numbers as input and subtract one binary number input from the another binary. Okay, similarly, we give two outputs. Okay, we call it as the difference and borrow. Okay, let's see. First is we have half subtractor. Okay, we have two types, half subtractor and full subtractor. The first is half subtractor. Okay, it's a combinational circuit which is used to perform subtraction of two bits. Okay, we have two input, we have minuend and subtrahend. Okay, subtrahend, and we have two outputs, difference and borrow here. Okay, we need M and S as the input, and this is at the next port. Okay, this is for logic symbol of half subtractor, and this is corresponding truth table. Okay, if we look at this truth table, okay, we should realize that the subtrahend of bit S here, okay, is subtracted from the minuend bit M. Okay, subtract from the bit M. So if we write 0 minus 1, the digit 0 is the minuend and the digit 1 is the subtrahend. If 0 minus 1, M is the 0 and 1 is the S. Okay, from this truth table also, we can derive logic expression for the half subtractor logic circuit. Okay, as we can see here. Okay, for difference and borrow. Okay, for borrow, we have B equals to M bar S, and for difference is M bar S plus M S bar. Okay, so this is the logic diagram. Okay. Okay, from these two equations, then we can draw the logic gates for half subtractor. Okay, for D and B. Alright, for difference, and this is for borrow. Okay, next is we have the full subtractor. Okay, it is a combinational logic circuit that perform subtracting, involve the minuend M and subtrahend S, and also the borrow in bit. We have another one B in. Okay, we have here. Okay, so this is the truth table M S P in, and this is same as the half subtractor. We have difference and the borrow B out. Okay, from the truth table here, okay, then we can derive the logic expressions for the difference D and B. Here we have the Boolean functions for full subtractor. Okay, for difference we have M plus S. This is exclusive OR and plus B in, because now we have another one bits in. Here is B in. Okay. In. Alright, and for borrow out, we have these expressions. Okay, and from these two expressions, we can have this logic circuit for full subtractor. Okay, for D, okay, MSB is the exclusive OR, and for B out is we use AND gate. Okay, we have one inverter here, and this is OR gate. Okay, so for this second subtopic, okay, for this section we have learned about the different types of adders and also the subtractors. Okay, so now we are familiar with the constructions and functions of quarter adders. We have half adders, full adders, and half subtractors, also the full subtractors. Okay, next we go for the canonical form of Boolean functions. Okay, we will apply basic rules of addition and subtractions. Also, we will do the simplifying Boolean equations, meaning that by using less variables and making it shorter. We need to simplify the Boolean expression, as this would eliminate the redundancy and also to become more readable. Simplified Boolean is also known as canonical form. Alright. So for memory and memoryless component, okay, the Boolean algebra is used to describe and analyze for combination logic gates. Okay, remember that combination logic gate is memoryless system. Whereas for sequential logic circuit, it is a memory system. Okay, why? We must simplify the circuit. Okay, we can save money, or we want to make the components fewer. Okay, so that we can save cost. Okay, we can also increase the circuit efficiency. Okay, since for fewer components are being used, less power will be consumed by the circuit. In addition, if something goes wrong, it is easier for the engineers or for the designers to troubleshoot and replace the components. Okay, the Boolean algebra presents us with the ability to depict and understand a digital circuit in mathematical form that it can easily be simplified. Okay, for memoryless system are also known as the combinational circuit. Alright. Okay, Boolean algebra is described to analyze circuit that are a combination of logic gates such as the system is memoryless. Okay, the input are independent of the historical sequence of values and presented to it as the input. Okay, the combinational circuit might be described in a few ways, such as we have a set of statements, and we can also express in the Boolean functions or Boolean expression, also in the truth table, and also we can have the circuit drawing or the logic gates diagram. Okay, first is we have the uh, sum of product. This is two methods of to describe the Boolean algebra. We have sum of product and product of sum, SOP and POS. Okay, first is the SOP. Okay, the function are defined by sum of product. Okay, each individual term in the SOP, we call it as the mean term, and we can write is like here. Okay, y equals to AB plus AC plus BC. So this is summation of product. Okay, this is one product, two product, and three product. Okay, next one we have product of sum. Okay, this form consists two or more or term which are we and it together. Okay. Each or term consists one or more variables in complemented or uncomplemented form. Okay. Each individual term in post product of sum we call as the max term. So this is the expression of product of sum. Post is we summation and then we product all the summation together. Okay. For SOP and POS equation, all the individual terms do not involve all three variables. Okay. If each term in both the SOP and POS forms contains all the variables, then the expressions are known as standard summation of product, or we also call this as the canonical summation of product and the product of sum respectively. It is all either we call as the standard or canonical. Okay, we can have the conversion, okay, from POS into the SOP, product from product of sum into the summation of product. Okay, the usefulness of the mean term and max term represents will become clear from the discussions. Like this one here, we have all terms are present in the final summation of product form. Okay, we have here is product of summations. Okay, and this is all the expression. Okay, to make sure no multiplication bracket exists after the conversions, meaning that we have multiplied all the components together. Okay, next is we want to convert from summation of product to product of summation. Okay, we can convert by using OR gate. Okay, this one, if we have this, we can summation all and we multiply. Okay, meaning that we must have the bracketing here. Alright, take for example a three variable expression with variable we have A, B, and C. If there is a term A where B and C are missing, then we form two term B multiply B and C multiply C, or A with this term. Okay, therefore we can get the expression. Okay. So, as a summary for this subtopic, the combination of mean term will form a summation of product, okay, expression, and the combination of max term will form a product of sum expression. If each term in SOP summation of product form contains all the variables, then the expression is known as standard SOP form or canonical SOP form. Okay, standard is equals to the same as canonical. Each individual term in the standard SOP form, we call it as the mean term. Okay, this one for next is minimization of Boolean function and combinational logic circuit. We will cover in unit 3. Up until for unit 3 up until VHDL. Okay, this one also in unit 3. So as for today, we have learned on Boolean algebraic theorem and its various laws for manipulating the Boolean equations. Okay, we have several laws which are simple equations like mathematical equations used to describe logic circuits with the aim to reduce the number of Boolean variables in the equation. Okay, we also have learned the logic simplification technique so that a Boolean equation can have fewer Boolean variables. Okay, next tutorial we will discuss on the K-mat technique and Queen-mat plus key technique. Okay, that one is on the minimization of this one. Okay. Alright, is there any questions from you guys before we end the session?
Yes, I have one question.
Okay.
Okay,